Hey all, this is Mr. Yeager for Honors Chem. Oops, sorry about that, already jumping off the wrong spot there. And we are looking at all the other types of bonding. So we covered ionic bonding already. We're going to look at covalent, acid naming, and metallic bonding. So yep, we're going to go through quite a bit, but this will move along pretty well, okay? So, with covalent bonds, this is where the electrons are being shared between the atoms. We'll again get into a bit more detail why that happens in the next video when we get more into the actual bonding character of it, okay? But a covalent is when they are shared. Remember, ionic is when they are transferred. These are called molecules, okay? And they're formed when we have two or more nonmetals combining, forming a chemical bond with each other. The nonmetals like to form covalent bonds. So metals and nonmetals form ionic. Nonmetals, two nonmetals together form covalent, okay? So obviously there's lots of examples of covalent bonding molecules, sugars, carbohydrates, fats. You can see all the other ones down there. We're definitely looking at much smaller molecules, but these are ones where with the sharing of the electrons we can create some very complicated structures. Okay? So the first kind of the simplest type of covalent bonds out there are what are called the diatomic molecules, and you can see them in my periodic table I have here. Highlighted in yellow. So there are seven nonmetals that, these are seven nonmetals that are never, ever, ever alone. You will not find a single hydrogen atom all by itself, an elemental hydrogen atom by itself. Same thing goes for nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, okay? And so that's why we have them there. What happens is they will always at least bond with another atom of itself, if it's available. Otherwise, obviously, you'll find it in other compounds as well. Clearly, they don't, it's not like they completely shut off everybody else, but they do like to pair together, okay? So there are seven of them. A lot of times what I like to say is there are seven nonmetals starting at number 7 that make a 7 along the periodic table down the halogens, and then we have to include hydrogen, okay? So, yep, I know that one's kind of just off by itself, but hydrogen as well. So this is going to be important when we start doing some chemical reactions where if we say oxygen is formed or hydrogen is reacting, etc., that means you're forming the diatomic molecule, not just a hydrogen atom by itself or an oxygen atom by itself. Some properties of covalent compounds. They generally have low melting and boiling points. They're usually gases. If they do form a solid, they're generally softer solids. There's exceptions, like a diamond actually is a covalent structure. That's the hardest substance in the world. But many other covalent compounds are much softer. When solid, they will form a crystal lattice, just like ionic, but it's going to be weaker. Okay, they don't form as nice a, I wouldn't say regular cubic, rectangular, structure like most ionic compounds can do. But they can still create some amazing lattices, which you can, an example would be snowflakes. Okay? And then we say that they're held together by what's called the bond dissociation energy. Okay? That's the energy in a covalent bond. As the name implies, this is the energy you need to dissociate, to basically separate those covalent bonds, those atoms from each other. So we call it bond dissociation energy. Okay? So, that's all the character. Now we're moving into naming. And I think a lot of people think naming covalent is generally, in some ways can be a lot easier than ionic, even though ionic's pretty straightforward. I think covalent compound formula writing and naming is generally an easier one for most students. So, what we run into with covalent compounds is they don't have any charge. So we need another way to determine the number of atoms. So we're not going to do positive, negative. If you think about it, nonmetals are negative ions, so we can't put two negative ions together. So we need another method to figure out how many atoms of each type are there. We use prefixes, okay? So we're going to have to learn our prefixes. Mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. All right? Those are the prefixes we just got to get used to. I always tell my students just practice by counting it out. Again, like I just did, mono, di, tri, etc., etc., okay? We can try to figure out those numbers very, very well. I think for the most part, many students do very well on this. A couple of them that I do see some people make a mistake on, tetra, okay? I hear people try to do quad. But tetra, if you've ever played the game Tetris, okay, Tetris is 4 lines, so tetra is 4. Some of the other kind of strange ones is hepta and probably nona, okay? You know, once we hit tri and on, we kind of think of objects that have that shape. So triangle, pentagon, hexagon, heptagon, octagon, nonagon, and decagon, and that's the number of sides we have. I'm only going to mention it just because I do have some students that mess up di. When I say what's a prefix for 2, they say bi, which is correct. Bi does mean basically 2, okay? But we use the prefix di, okay? So mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca, okay? So how do we then use this? Here's an example, S2O4. First off, that's covalent because non-metal, non-metal. Sulfur and oxygen are non-metals. The first element will keep its name, and then you use one of the prefixes to show the number of atoms. Okay? We do not use mono on the first element. So if there was only one sulfur, we would just say sulfur, not monosulfur, if it's the first element. Okay? So mono is never used on the first element. The idea is, if we say it out loud that there's sulfur, we know that there must be at least one. Now you have to tell me if there's more than one by saying, in this case, disulfur. The second element will get the suffix "ide" and we'll add the prefix to show the number of atoms. So the second element can take any prefix including mono. So the one up there is disulfur tetroxide. A lot of times with oxygen and a couple, you know, we might run into this with occasional other ones. We often don't double up on the vowel, so we're not going to say, you know, tetraoxide, okay? You know, we do run into it with I. We usually keep the I like dioxide or trioxide, but usually when there's an A on it, we eliminate the A, okay? Instead of tetraoxide, it's tetroxide. So some examples over here, OF2, that would be oxygen difluoride. We don't use mono. C6H6, hexacarbon hexahydride. Ooh, hydrige. Oops, that's a bad spelling. Sorry about that. Welcome, hydrige. Okay, hydride, hexacarbon hexahydride. Okay, and then N5I7, pentanitrogen heptaiodide. Okay, and so there you go. I mean, a lot of times it's pretty straightforward. You just got to remember that. I mean, you got to just remember the prefixes. That's basically the main idea. Name the formula. Well, if you know the prefixes, you can name in the name. That's all you got to do. Okay, the prefixes in the name is telling you what to do. So, tricarbon nona bromide. Tri is 3, nona is 9, so this is C3Br9. Okay, carbon tetrachloride. Carbon, that's just 1, so CCl4. Okay. I mean, that's it. I know I'm not doing many, but that's essentially it. Yes, it's a lot of syllables. It's a large name, and that can be kind of frustrating when you're writing a lot of them down. But hopefully, as long as we know those prefixes, we're good to go. Okay? Acids. Acids. All right, we're going to just talk about this a little bit right now. So, with acids, they react with metals. That's what you see in the GIF over there, where the acid's basically breaking down the metal there. Okay, quite a bit. We also have a base breaking it down some. All right, it involves nonmetals, but they have. Sorry, let me say this again. Acids many times involves 2 nonmetals coming together, primarily looking at hydrogen, but there's a large enough difference in electronegativity that they actually will have a charge. We will be talking about this having H plus and Cl minus and so forth. Okay, so we'll talk about that in a moment too. There are 2 types of acids. We have what are called binary acids. They have hydrogen and another nonmetal. And then there's what's called oxy acids. They have hydrogen and a polyatomic ion with oxygen. So in other words, they have hydrogen, and then it's either an element off the periodic table or it's an element off the polyatomic sheet. Okay? So when naming a binary acid, just an acid with 2 elements, HF, we would begin this with the prefix hydro. So this will be hydro, okay? The anion will get the prefix ic. And so we just put those 2 things together. Finish with the word acid at the end. Polyatomics without oxygen will also follow the above rules. That is really only the Cn minus, the cyanide ion. That's the only one you got to be careful of. We would change it to cyanic, okay, because it's polyatomic without oxygen. I know that means it's not a binary acid. It'd be called a tertiary acid then, meaning 3 elements, but it follows the same rules. Okay, the compound above is hydrofluoric acid. Hydrofluoric acid. So again, this is because I only have 2 elements. It begins with hydro, anion will end with ic, and then acid. So some practice ones. HBr, 2 elements, hydro, Br is bromine, so bromic, hydrobromic acid. Okay, H2S is hydrosulfuric acid. Hydrosulfuric acid. I do hear people try to say hydrosulfic. So sulfur is one that we keep the whole name and we still add the prefix to it. So hydrosulfuric acid. H3N is hydronitric acid. All right. So I mean, you can pretty much go through all of them that you're going to do. Fluoric, chloric, bromic, iodic. O we really don't run into because H2O is water. Okay. S hydrosulfuric, Se hydroselenic, N hydronitric, P hydrophosphoric. All right. We can even do the AS, which would be hydroarsenic acid as well. Okay. Naming oxy acid. So this is probably a little tougher part about acids, is you have to first notice whether it's a binary or oxy acid. And then we have this little phrase, A to ic, I to us. A to ic, I to us. Okay. So my example I have is HNO3. So I see hydrogen and I see a polyatomic ion. We do not use the hydro prefix now. If I have a polyatomic with oxygen in it, there's no hydro prefix. What I do is I look at the polyatomic. If it ends with 8, I'm going to change that to ic. A to ic. If it ends with ite to us. O-U-S. So that's something you got to pay attention to. You have to look on your polyatomic sheet and go, is this something 8 or something ite, and change it appropriately. So the one, and then we add acid afterward. The word acid, that takes care of the hydrogen, because if it's acid, there must be a hydrogen involved in it. So the one above is nitric acid, because it's nitrate, A to ic, nitric acid, and then we're done. So no hydro means I'm taking a polyatomic ion and not an element off the periodic table. Okay. Some other examples, H2SO3. SO3 is sulfite, so it's going to change to us, so this is sulfurous acid. H3PO4, that's phosphate, so that would be phosphoric acid. H2C2O4, that's oxalate, so A to ic, oxalic acid. All right, but we never use hydro because it's a polyatomic ion. Name the formula. So going now to where the heck how do I know how many hydrogens there are in the atom? Okay, so we're going to use the word we're going to use the example nitrous acid. So right there, there's no hydro, so this must be an acid that has a polyatomic ion. It's an oxy acid. Okay, we know it's going to start with H, but then we'll figure out the last part. So you see acid begins with H. Do you see hydro? Okay. If yes, find the anion off the periodic table. In this case, I don't see hydro, so no. Again, exception cyanide, sorry about that. No, identify the polyatomic ion, not cyanide, the oxy acid, again, the polyatomic with oxygen. All right, it goes back to 8, us goes back to ite, so we basically do the opposite. So if I look at this particular compound, this is nitrous, so I'm looking at nitrite. Okay, so the above one is HNO2. Okay, HNO2. All right. So one thing I did not put on this is how do I know there's only one hydrogen? Basically, the number of hydrogens equals the charge of the anion. So nitrous is NO2 minus. So this is just going to be one hydrogen, okay? And you'll see other examples in a moment, okay? So hydroselenic acid, I see hydro. That means I'm looking at the periodic table. Selenic is selenide, or selenium. So that's Se. Se has a -2 charge, so H2Se. Okay. Phosphorus acid, no hydro, off the polyatomic. This is PO3, 3-, so I need 3 hydrogens, H3PO3. Perchloric acid, HClO4. Sorry, I went a little fast there. No hydro. I'm looking for perchlorate, ic to 8. ClO4 is chlorate, -1, so 1 hydrogen. Okay. Hydroiodic acid, back to off the periodic table. Iodic is iodine, -1 HI. Okay. So that's basically it. Again, the number of hydrogens in the acid is just equal to the charge of the anion. Last type of bonds, metallic bonds. These are bonds formed between 2 metals. So again, I'm doing this because we've done metal, nonmetal is ionic, nonmetal is covalent. So what about metal-metal? So metal-metal is just simply a metallic bond. We already went through quite a few of the properties of metals. They're good conductors, they are malleable and ductile, they have high melting and boiling points. So this is basically a single metal atom that's combining with a bunch of its kind, so a bunch of iron atoms all coming together, it's iron. Okay? So how or why would metals bond together? Basically what we have is we have this phrase called a sea of electrons. So metal atoms generally are generally larger, mainly looking at the transition metals, and they have those d orbitals involved. Therefore, these d orbitals all overlap, and all of those electrons come together. Okay? These electrons, we say, become delocalized. All right? All the little blue dots are the electrons. So the idea is I don't know exactly which of these metal atoms, these metal cations, are attracting those electrons. So we say that they're delocalized. And what happens is basically all of these metal atoms gather in amongst all the delocalized electrons, and they're attracted. Basically, we have the positive nuclei all attracted, all these atoms attracted because of all of these electrons, and they're going, hey, I'll share some of these. It is almost a sharing mentality, but they're not completely shared. They're clearly they're moving around all of the metal ions. So we call this a sea of electrons because it's like I have the metal and I'm pouring all these electrons over them. That's keeping them together. So the key words for metallic are the sea of electrons and delocalized electrons. Okay. Naming rules for metallic bonds, there are none. Okay. That's because basically I'm saying, like I mentioned before, I'll have this iron, I'll have this iron, I'll have this iron, and I'll have that iron, and I'll have that iron, and then all the electrons are all around it, holding these iron atoms together through metallic bonding, and we would just call it iron. Okay? So that's basically it. All the metals are that way. Platinum, a bunch of platinum atoms combine through metallic bonds to form platinum. Okay? That's basically all we're looking at. So nothing special with the naming. The last thing to kind of share with metallic bonds is they are involved with basically forming alloys. All right? I don't want to say forming because, again, we do have the mix. This is a mixture, so we're not actually forming chemical bonds between them. But when we do have alloys, we basically are mixing in some of these other atoms that might then be sharing the other electrons, but they hold their own properties still. So we have what are called substitutional alloys, where essentially we replace one type of metallic ion for another one that's similar size, and so basically they all still fit together. It looks like Connect 4. All right. So this could be bronze, where the blue ones are copper and the other ones are tin, or the red ones are copper and the blue ones are zinc, and then all of a sudden we will have what we call brass. But it retains the properties of both copper and zinc. It just is able to combine kind of those properties together. We also have what are called interstitial alloys, all right? And this is where smaller atoms fill in areas between the metal atoms, and those spaces are called interstices, all right? It's just like if you try to draw 4 circles, there's going to be a space between all 4 circles. We can put tiny, tiny, tiny atoms in there, and that will fill the gap and strengthen the metal, because now there's no more, it basically makes it more rigid in a way. So that's how steel is formed, where iron could be those red atoms, and then carbon is the blue atoms. Okay, so there's some steel. So that's just some additional information about creating alloys, and obviously some metallic bonding occurring between the atoms still. Okay, and that is it. Thank you very much.